Okay, so we are live. Hello and welcome everyone, whoever is joining us for this DSTI live event. We are on LinkedIn, we are live on Facebook, we are live on YouTube, and we are live on X. So welcome whoever is joining in. This is a specific program to highlight one of our own star students, one of our past students, Jannic with us. We are thrilled to introduce him today. And Yannick was a student in our applied MSc in data engineering for AI program. He was enrolled in self-paced online course that is SPOC mode. And while he was learning with us, he was preparing for his data engineering course. He had some remarkable uh, technical and professional achievements that are quite inspiring. I'm pretty sure that you will all be inspired by his work. Also, we are going to ask a few questions about how his journey at DSTI was. Why did he choose DSTI? What difference did DSTI made? And ultimately, did he achieve his goals or not? All right. In addition to Yannick, I also have with me Hannah. Hannah is professor and vice dean at DSTI. He sits at Paris campus. And myself, I'm Neeraj Devbhankar, and I will try and host this event in between. Uh, welcome all. So, before we get into anything, Yannick, could you probably talk a bit about your background?
Yeah, I'd be happy to. Thanks, first of all, for having me and also for the very kind but dramatically overstated introduction. Though I'd be happy if some of what we can discuss today may be of interest for some of our listeners. As you mentioned, my name is Yannick. Um, I am actually not a data engineer originally by training, but I started my academic journey some, what is it, 15 years ago now in economics. So I was always very interested in, let's say, social science questions, in particular in the realm of economics and finance. So those of you that are a bit older, my generation or above, may remember we just had this financial crisis and had to use taxpayer money to save broken banks, right? And I was asking myself, how can this be, right? How can we create a system that works better for everyone so we don't have to privatize all the gains and socialize all the losses? And these questions were kind of driving my decision to study economics. And I was early on in my economics education realizing that the part that I enjoyed most during studying economics was really the kind of data work, right? So not just
Mhm.
the theory, not even just reading the books or reading the papers or discussing economics ideas, but really getting your hands dirty with the data. And yeah, so then over a course of a bachelor's, master's, and eventually PhD, I turned into ever more data-centric work. Two of my PhD papers were already quite, let's say, data engineering and AI heavy. And then after I graduated from my PhD, I was looking for options of what I want to do, and I mean, there were several on the table right after you graduate. It's kind of the point in time where you have to figure out what is it where you want to go. And for me, I started a internship basically at the European Central Bank, which is the monetary authority for Europe. And originally, I started on the business side, and that was a very nice, how should I put it? It was a happy coincidence of once, as the economists put it, because most people on the business areas, they really like to discuss the economics and make the presentations and really learn about how things work in, let's say, financial regulation or whatnot. But using these huge data sets that became available at the time, so we're talking about terabytes and terabytes of highly granular exposures of financial institutions and whatnot, this posed quite a challenge, right? Because it was not the kind of data that you could work in Excel or even in, let's say, Python or natively on your own computer, right? You had to leverage some way or shape or form of cluster computing solutions, which of course is very much at the heart of the typical data engineering topics. And over a course of was been now like 2 years on the business side of the ECB, I then switched towards more software engineering. So really joined our IT division because I realized that for me, while I always find these social science questions very interesting, I like working in a field where you do something and then it works or it doesn't, right? And you get an extremely precise answer. And computer science, programming, data engineering is something that gives you that. Whereas if you work in core economics, there are always different ways how you can look at things, right? It's somewhere in between a science and an art. And to me, in my mind, just I'm more an engineer, right? So making this transition a bit away from core economics towards more software development, data engineering type work has been a very, very rewarding journey, of which DSTI has been a part for the past 3 years now, I think, something like that. And I'd be happy to get into that a bit more today.
Awesome. So before I hand over to Hannah, I would like to again remind everyone who have recently joined us that this is Jannic, who we are talking to, and we are talking to about his journey in at DSTI and how it helped them. Uh, Benny says hello everyone. Hello to you too, Benny. Uh, Thank you, guys. We would really appreciate if you can comment, if you want to comment, if you want to ask questions to Yannick about his experience at DSTI. Also, he is going to talk about couple of his recent achievements, right? So over to you, Hannah. Probably we will start with. I'll handle this part. We'll start with IEEE. Is that right, Yannick?
Yeah, that's perfect.
Yeah. Yeah. All right.
Okay, yes. So if you have had a look at the DSTI curriculum, you probably saw that a Python machine learning labs is one of the classes. And as with many DSTI classes, you can have a project in the end as an evaluation. And while there are always off-the-shelf projects, you can also pick a project yourself. So for this specific class, which was taught by Hannah, I chose to participate in a competition that was hosted by IEEE. So IEEE is one of the main computer science, electrical engineering associations, and they host multiple conferences a year. And in those conferences, you can apply with regular research papers, but they also have these kind of competitions where if you do very well, you're invited to basically write a technical report of what you were doing and publish that as a paper in the conference proceedings, which is what I was able to achieve in this project, in this class. And before I get into the details of it, I have to make one disclaimer, actually two disclaimers. First of all, as you may see on my LinkedIn or other sources, I now work at the European Central Bank, and as such, I have to make a disclaimer, right? Any view that I present here is just my personal opinion, and it should not be represented as a view of the European Central Bank. So that's the official disclaimer. And then secondly, if you want to go to the next slide, Niraj.
Yeah.
This work is not just my own, right? I'm deeply indebted, first of all, to Hannah for the amazing class, which I learned a lot. But then, secondly, also importantly, to my co-author Stefan, who has been instrumental in this work. And I should also note in this regard, any project, any meaningful project that you ever work on, very likely, if it's truly something worth doing, is not something that you can do alone, right? And this means that you have to have some specialization. So, for example, on this project, Stefan was really a bit, let's say, the AI engineer, and I was a bit more the data engineer. This also implies that I will be more than happy to answer any of your questions. But if there's something that I don't remember anymore that was more in Stefan's area of expertise, maybe Niraj can liaise that we can exchange later some more information about that.
Yes, of course.
But with that, let's jump into it. Okay, we can go on that further. We can talk a bit about muon tomography. There is some timeline here that's not too important, so let's get right into it. What is muon tomography? If you have no idea what that is, you were just where I was a couple of months before I started that project. So muons are part of the cosmic background radiation. Yeah, think of it almost like light particles. So they hover all around us. There's about one muon per the size of my hand. Okay, so you face the size of my hand palm, right? There's about one per second crossing through, and they're all around us. Extremely small, so you can't see them, right? But they're all around us, and they can be utilized in order to do object detection kind of tasks. Okay. So here in this graph, what you can see is you have some object here placed in the middle, okay? And then we have two sets of detectors that we can put there. Niosh, can you go one further?
Yeah.
Right, we have these two sets of detectors, and these detectors will be able to register one of those muons crossing through them without deflecting them, right? So you just know, there was one of those guys. Okay, can we see that on the next slide? Okay. So now what we can see here is, right, we have two sensors above and two sensors below an object in the research space, and we basically have the three-dimensional location of these muons in the research space. And what the idea here is that as these muons pass through heavy materials like gold or metal or these kind of things, they get deflected on their path, right? If you were trying to interpolate just mentally, how did this thing go through, then it's probably something like this, right? Okay, and this is represented basically as data in this table here, where you can see we have above 1, above 2, below 1, below 2, which is just the 4 sensors that we have. And then we have an X, Y, and a Z coordinate for the location of where the sensor registered one of those muons, right? So if you think about three-dimensional space, okay, 3 dimensions, dot, 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 dot. Okay, that's the data that we have, right? And now what does that mean? Okay, we have these registrations for about 15,000 training examples. And a training example is one of those guys where this is now basically the bird's eye view on objects in the research space. So it's a bit difficult with the color coding because there were so many different metals, but all these colors are on the right, right? It's a shorthand chemical notation for a metal. And you can see the shape where something is sitting there, okay? So let's say this is example 1. For example 1, we have 40 to 45,000 of these, well, multiple tuples, right, of sensor registrations, right? Okay, now the task is, if I now just give you the X, Y, Z, right, these 4 X, Y, Z things, but I don't tell you what's in the middle here, how can we predict that? Can we use that? And that, of course, if you think about it, if you were able to do that, that would be very, very valuable, right? Because it would allow you to do non-invasive scanning, right? So you have some object and it's maybe, I don't know, copper on the outside. You can just tell by looking at it. But maybe there is gold inside, or maybe there is something radioactive inside and you don't want to be near it, right? So being able to use this information to study the interiors of object would have a range of industry applications. So how do we do it? Well, the easiest thing would be we look at an incoming vector, okay, and an outgoing vector. And the idea is now to say, okay, there's a difference between the two likely, right? And this we can calculate. This is just the deflection angle, so to speak. And as let's say the object, the moon is just moving through something like air or water, there's not going to be much of a change in the vector. But if there's some heavier metal, it might be deflected quite a bit. Can you go one further? So the idea being again that matter in this research space will deflect the muon's course, right? And you can work out the math to see that this equation holds to calculate it. Okay, so with this, the next thing that we did was to say, okay, so what do we have for one example? Okay, so one, let's say, input configuration of materials that's sitting there. Let's try to see how many muons are registered at the z equals 0, so in the research plane space, just in the different locations. So this is what we see on the left. We can see they're centered a bit in the middle. Okay, that's probably useful because these materials tend to be in the middle. And then on the right, you can see the scattering angle, right? So that's how much these muons get deflected on average in any given cell. You can imagine here I have a 200 by 200 grid, but I have 55,000 muons passing through. So there might be more than one in one given cell, as we see on the left, and then we average that a bit, right? And here on the right, you can already see a little bit what's going on, right? So on the lower left, I can see some shapes, the top, middle, and then somewhere on the right in the middle. There's maybe something going on there, yeah? So let's go to the next page. And on the next page, you can see on the left what is basically what we calculated using just these coordinates as an input and the ground truth. Okay. And just looking at this visually, right, you don't need to be an AI expert to see, okay, maybe something's going on here, right? At least let's say the shapes of the object that are placed in the research space are plainly visible, right? The stuff that you can see on the left, the stuff that you can see on the right, that aligns quite neatly. And all this already achieved without using much AI, right? So speaks to the value of proper data pre-processing. Because that there are some more details that I'm skipping now, but actually just getting to this stage, data cleaning is a bit of a challenge here. Okay, but anyways, let's say we have now this grid, right, of these, let's say, average angles or whatever, right, in any given cell, and we know that this is one of 22 materials. And this is on a, depending on how you do it, there are different ways, on let's say 40 by 40 and 40 by 40 matrices with these values. I mean, this almost screams neural network at you, right? Because there will be likely some very nonlinear effects going on. And this type of, well, let's say image processing is one where, yeah, neural networks just really lend themselves to. Now, for any neural network, let's go back one slide just quick. For any neural network, or any optimization task, really, the thing that you should care about is, well, what should you care about? It depends, right? It depends on what you want to do. So typically, one of the first things you learn is something like accuracy, right? Accuracy just being, okay, how many data points do I get right? Okay. So if you do the math in this problem, if you just predict there to be air everywhere, there's no object nowhere, you would have an accuracy of 85%, which is amazing, but completely useless, right? What you actually care about are these fields where there is something there. And to cater to this, we use the custom loss function, which is one that's typically used in this field, which is called the mean average intersection over union. So you can see the formula in scary math on the left, but on the right, we try to visualize that, right? So if you think about, you have some prediction and you have some ground truth, you wonder, well, what's the intersection? So where do we align, and what's all of it, right? And clearly, as your prediction and the ground truth are more the same thing, the intersection over union measure approaches 1, which would be the best you can reach, right? Okay, now we have a function. Now we need to throw that into some kind of model, and then we let PyTorch or TensorFlow or whatever is your neural network modeling framework of choice do its magic, right? And this we can see on the next slide. So a typical architecture for object recognition in graphs. So let's say you have you have some, I don't know, the canonical example is probably you have an image on the street and you want to classify, there's a car and there's a pedestrian and there's a red light. Yeah, this we've all seen in some machine learning course online, right? And a typical way to do this is so-called a U-shaped model or a U2-net approach, right? Where you start with a very big input layer, and then you slowly scale it down, and then you scale it up again, right? Basically, you go down in the resolution, but you increase the depth of it, right? And since our input data was, I think, 400 by 400, but our output data was 40 by 40, we jokingly labeled the paper "Breaking the U" because we don't really have the U, right? On the second hand, we only have half the U. And yeah, this basically is then the network shape that you can quite easily implement in Python. I don't remember. I think we used PyTorch. No, we used TensorFlow in the end. Throw in your custom function, and then hopefully have a GPU available to you, because this shit takes long to estimate, right? And that gives you then the output matrix of 40/40, right, for each example, with the 22 channels, where each channel then represents one of these materials probability in the softmax term, right? Okay, so here on the left, I mean, these are two of the more classical machine learning type plots that one would expect here, right? So training and validation loss for our for the sample data that we have, quite noisy initially, but then they converge. And if you think about the confusion matrix, right? So the confusion matrix is how well did you classify each individual one? Ideally, you would have this diagonal completely blue. You see, we're not doing too bad. I think the next slide is actually even more instructive of what we do well, what we don't do so well. So here on the left, you can see the 22 materials. Just have the numbers down there for now. So 0 is air. That's why that bar is so large, and I kept it actually at 35. And you can see air we almost perfectly predict, right? So this is like the red dot there on the right-hand scale is basically a 1. So the shapes we get right. Now the materials, depends a bit on the material, right? Most of them we have an accuracy above 60%, but there are 3 of them. They're also in the footnote here. I think silicium. Okay, I don't know the chemical shorts. Let me not pretend I do. So those 3 of them, we didn't predict them very well, which would be an interesting, further line of research to understand why this didn't work for those, right? In order to, yeah, okay. So overall, the conclusion I would say here is that muon tomography can really benefit from deep learning, right? Since we're able to predict the shapes pretty much perfectly and a lot of material already quite well. But there are some challenges remaining. First of all, some materials we didn't predict well. And then, of course, depending on the industry application, an accuracy of 60%, 70%, 80%, even 90% is just not going to cut it, right? For some industry applications, you need something like 99.99. And clearly, we're not there yet, right?
Yep.
Yes. Anna, please.
Yep.
Thank you, Jannic. Sorry, Niraj, I'm going to intervene because I just wanted to thank Jannic for the expose, for running down a complete deep learning pipeline. So this is typically one excellent example of what we do in any kind of data project. But I wanted to come back to something you said early on, Jannic, and that we didn't really focus on. And it's outside the slides, by the way. It's the idea of the data preparation, how important it is, because this is something that a lot of people who are interested in AI or in data in general or in data engineering even don't know or neglect. They think about the models. They don't think really about the data. And I think from what I saw from the work that a lot of the work that you and your team, of course, have done was on the data itself. So can you just very briefly, in a few words, tell us how do you prepare for a project where the data is this big and challenging? What is the approach? And a little bit maybe add a few words about the specificity of what made your data preparation so good for this project.
Yeah, sure. I think I did actually add one slide at the very end because initially I prepared the slides for IEEE and then they didn't care so much about data preprocessing. But in the very end, if you go further, yeah, this one I just added for you guys. But so we can go over that in a minute. But to answer your question, I think there is 2 things. First of all, there is, let's say, domain knowledge, domain expertise, right? That you have to bring to these projects. So when I first looked at this data, I was looking at these coordinates, and what I didn't show you was you also had the energy level of the muon before and after. And I looked at this and I was like, sure, it's the energy. I'm just gonna look at the difference between energy before and after. That's gonna tell me everything. And then I thought, I know, maybe also the angle. And I did a back of the envelope calculation, how much of deflection there is. And it turned out to be minuscule. It's really not a lot. It's not like 2 or 3%, or like in the graph, it looks like this. It's not like that at all, right? For the human eye, it would not be visible. And I thought, it's not important. Now, turns out in the domain of physics, such small angles are very important. Yeah. So this kind of domain knowledge you have to bring in, and then really get your hands dirty with the data, right? If you work on such a thing, and someone asks you, well, what's your average angle in that data? Yeah, you have to know this stuff, right? That's the one thing. The other thing is a bit more technical, and more in the really core data engineering landscape. And this is also something that's very often forgotten when I look at these kind of projects. And it's something like this, right? So we have 60 gigabytes of input data here with about 900 million rows of these four XYZ tuples, right? So here on the left, I've written down for you what the naive data scientist would do, which is what I started with, because it's quick, right? You can go somewhere. So you read it in with your pandas or R or whatever your language of choice is, and instead of looking at this data and thinking about it first, you immediately start coding something. I want to calculate something. I want to see my result already, right? Now, why is this not a good way of working in this case? So if you just read in the data with out-of-box pandas, you can do data analysis, but it's inefficient. So for example, in this case, the way the data was represented would make pandas read it in as a float 64, right? So you can see at this example, 0.158 is 0.0000000. But if you look over all the data, you see each of these coordinates just really has 3 decimals or 3 integers, or right, like there's not actually that much information that you need to put it in a float. So instead, just transform that to an NP16 int, and just by doing that, the amount of memory that your Python session requires is cut by 75%, right? Now, this is the data that you throw into your ML AI model or whatever you want to use, which is of course drastically reducing the memory footprint and thereby, easing your resource requirements that you have for it, right? And then secondly, what we did here was we looked into data storage. So the data was given to us as CSV files, comma separated values, basically a text file, which again is not really ideal way to handle such big data sets. Instead, what you may want to use are technologies like Parquet, which are very efficient file formats if what you care about is columnar storage, which is to say you care about being able to access individual columns of the data, because you can make use of things like run length compression, which can further drastically reduce both the footprint on your hard drive, which maybe today so you don't care so much about anymore, if we're honest, but it will drastically speed up the reading of that kind of data, right? So I'd leave it at that, but of course happy to follow up if you like.
Thank you, Jannic. Niraj, maybe we can look at the second of Jannic's projects.
Absolutely. We move on to the second project of Jannic.
Yes.
In the meantime, before we go there, I would like to just remind everyone, whoever is watching us on YouTube, on LinkedIn, or Facebook, or X, you could ask your questions to Jannic. They could be technical questions. They could be questions about DSTI, his experience about DSTI. We are going to come to that particular part once this particular, this presentation is done with. So you could ask your questions, and we'll definitely ask your questions to Jannic for you. Thank you. Yes, Jannic, please.
Yes, with that we get to the next one. So again, this is the result of a project that was the final evaluation term project for one of the classes at DSTI. I forgot the name now, but also one in the AI space. Was it? This one was the Python machine learning labs. The one from before was actually deep learning. Now I have it figured out. So this was Python machine learning labs, and it didn't really have a title yet, so I just called it multilingual deduplication, because what me and my co-authors on the next page were attempting here was we participated in a data science challenge that was hosted by Eurostat. So Eurostat is the European Statistical Agency, and they collect all sorts of data. And they hosted a competition where they tried to get some help to solve the following problem. Okay, so in AI, everybody knows about forecasting, but believe it or not, at many statistical institutions, we actually also care about nowcasting. So nowcasting is answering the questions of what is today, right? If I ask you, like, what is the inflation rate today, or how many open jobs are in the economy right now? The information is in principle out there, right? It's not about predicting it really, but it can be difficult to get, right? In particular, a lot of those numbers that public institutions care about, they are available, but only available with quite a lag, right? And we love to have timely information in order to do good policy decisions, right? So how could you learn about the open positions in the economy? Well, you could go to, like, let's say LinkedIn and Xing and all these other platforms, and you could just web scrape the shit out of them, right? Just get everything that's on there, and you have an almost real-time feeling for the positions in the economy. But there is a problem here, and that is one of data duplication. If you're a big company, so here, for example, have Mercedes-Benz, if you could go back just once more. If you're a big company like Mercedes-Benz, right, and you have a given position, you might advertise that position on several different of these platforms. But there is no unique identifier across those platforms, and there might even be, in terms of the text that you use, some slight differences, right? You may have Mercedes, Mercedes-Benz, Mercedes-Benz Finance, AG. The title might be different. I mean, what's the difference between a financial analyst and a finance analyst? I don't know, might be a lot, might not be a lot, right? And then just to make it even worse, it might be in different languages. So you can see the fourth language here is my language, German, right? And you have this, and if you now take this table, right, where you have all your web scraped stuff, and you would look at how many rows do I have and claim this is the number of open jobs, then you would be wrong. And to make things worse, you would be wrong systematically, right? Because every time you're gonna drastically overcount the number, the true number. Okay, so this challenge was about how to deduplicate that. What Eurostat wanted to have was to say, okay, job ID number 1 is actually the same job as 15 and 2,445 in the data set that we have at hand. Okay, the data set that we have at hand is a bit shown here on the next slide. So there were 112,000 individual job postings in 25 languages and quite unbalanced data, a lot of missings, extremely dirty data. I mean, in the last presentation, we talked a bit about the importance of data cleaning. Man, in this project, it was really 50% of what we were doing, if not more, right? Because there are HTML text in there, some other web scraping artifacts that end up in your data, and it was just a horrible mess, right? You do a lot of time just making sure you have sort of clean data. Okay, once you have that done, at least a little bit, you have some specific challenges. The first challenge I would call computational complexity. So if you have 112,000 postings, you would technically need to compare each one against the other, right? So you take one, you look at another one, and then you decide, is this a duplicate or not? So how many comparisons do you have to do? Well, it's n over 2, which is 6.2 billion, right? Now, this is extremely problematic because comparing text is expensive, irrespective of how you do it. It's either expensive or very, very expensive. And if you think about it a bit more computer sciencey in terms of algorithmic efficiency, this is n squared, right? Which is almost as bad as it gets, right? So clearly this is one key challenge. Next key challenge, many of the classical NLP techniques, natural language processing techniques, such as bag of words, Levenstein distance or whatnot, really only work if you have just one language. But here we have multiple languages. And then additionally, in this challenge, it was not just about duplicates, but Eurostat had different types of duplicates. That one they call full duplicates that are really identical except to very minor formatting issues. Then there were semantic duplicates, which is to say just different wording for the same thing or even different language for the same thing. Then temporal duplicates, which are either full or semantic, but with different retrieval date. And there are partial duplicates. I'm telling you, to this date, I still don't understand what the partial duplicates were. We scored extremely poor in that category, and so did all the other teams. So I'm going to ignore that for the rest of the presentation. But if we go one slide further, one thing that I want to highlight here again, just on the data cleaning, was that 87%, well, first of all, 100% of the full duplicates we were able to identify, which wasn't that hard, to be honest. But of the temporal ones, also 78% were of the kind where just doing proper cleaning, we were able to get the correct numbers, right? So again, data cleaning and really understanding the data that you have at hand is very important. But now to the more nitty-gritty AI bit, right? Okay, so we have multiple job postings and we have the challenges in mind that we had. We need some strategy what to do about it. Okay, so here's what we did about it. You take a job posting and you throw it into a transformer model. So you've heard of transformer models like BERT, like with the earlier generations, right? Now we have, of course, ChatGPT and all these things. And what they will do is they will give you a vector representation of the data. So instead of some text, you now have a very long and typically dense vector, meaning a lot of zeros, and then some numbers in that represent that information in respect to all the other job postings in your corpus. Okay? This is on the middle part, and now on the right part, you see the search object, right? And this you can also put in an embedding model. So now you have these two vectors, and two vectors are just two sets of numbers. This I kind of know how I could compare, right? I could do things like Euclidean distance. So at least this multi-language or text comparison problem, the embedding model already sort of solved for me. But I still have the problem that, okay, I have one, I need to compare them against all the other, and the second they compare against all the other. So the complexity problem is still there. And what helped us overcome this was something called fast AI similarity search, or Facebook AI similarity search, because it's the Facebook guys that came up with it. And what this allows you to do is you put all of those vectors in that FAISS document store, and then it will allow you to retrieve in linear time the 100 or the 100 or however many you want nearest neighbors for any given search object that you care about. Okay. Now, if you want to look into the details of how FAISS achieves that, we have on the GitHub repository a link to their original paper. It's quite technical and complicated, so I can't really go into it much today because whatever I ever understood about it, I've forgotten in the past year. But it's a cool paper, and it's solving a great problem, right? Because if you go down from n squared to n, that is pretty amazing. And we were able to put this basically together to find, let's say, some candidate matches. Okay. So for each job posting, we retrieve the 100 nearest neighbors. So this means we're now down already 99% of the possible comparisons we don't need to do anymore. And of the remaining ones, again, domain knowledge was critical, and we applied some expert rules of different phrasings and wordings and whatnot in order to arrive at the final result that we were looking at. One particular challenge here, just by the way, was that we didn't have the true labels, right? So it was an unsupervised machine learning problem. But if you go to the next page, I still do have some statistics here to report. I meant to have footnotes here. So this is F1 and accuracy that you can see in the table. Now, how do I have that information if I don't have labeled data? Well, as I mentioned, it's a competition, and we were allowed to make up to 10 submissions in total. And Eurostat would give us this kind of feedback, so we had an idea where we are going, right? And yeah, you can see the full duplicates we got quite well. On the other one, yeah, it depends a bit. We did have an optional step of translating into English first using Google API, and then applying an English-only model, which tend to be, well, better calibrated, right? Versus a multilingual model, and we do find that translation step actually helps. But yeah, but the interesting bit, I think, of this entire project is really this two-tier architecture of use an embedding model, and then you put the stuff in FAISS to overcome both this multi-language problem and the computational complexity problem. And yeah, overall, I'm really happy that this project worked out so well, because it ranked us second for accuracy. So one team beat us just narrowly, but we were ranked first for reproducibility. And overall, we're awarded 13,000 euros of prize money, let's say, for these competitions, which is of course a nice upgrade for your student life.
I'll let you catch your breath, Jannic, because you've been talking nonstop, and just say here that again, this is a good example of when you put good practices, good data practices in place, you can actually go very far. So congratulations again, well done on the job for you and the team. You guys got a great result. You even won some prize money, which is a very nice added bonus. But it's just to see that putting together some good data practices often leads to very good results. We can do some very good things with that, and this is what we try to repeat at the STI. I don't know, it's been some time for you, but I don't know how much you remember in the STI courses. We've been stressing a lot on this idea of data. People rush toward the models, but actually, if the data preparation is not good, then whatever model you use will never be good enough. And this is an excellent example of what we keep saying at the STI. Thank you for that.
Yeah, then on this slide we have some limitations, but it's a bit more on the technical note. So I mean, I don't think we have to go into details now. Then here, this I hadn't copied over yet. Yeah, so okay. This was erroneously still from the other presentation, but yeah, okay.
No worries. Maybe we can just quickly bridge how whatever you've seen at the STI and what you learned from your training, from your self-training, as well as an economist turned data scientist turned data engineer, helped you towards achieving these two projects and other things that you're doing in the data engineering field today. So if you can quickly talk a little bit about that for us.
Yeah, definitely. So I think there was two things you asked about, right? On the one hand, DSTI, and then on the other hand, my previous life as an economist, right? My old life. Yeah, let me start with that one to stay chronologically. So I would say one thing that really you learn during a PhD is you take ownership of a problem, right? Because in the end, really, no one cares when you hand in that thesis. If it's 3 years or 4 years or 5 years or 8 years, no one at university really cares. Quite the contrary, because they have used cheap labor force to do teaching, right? So if you don't push your own way forward in academia as a young PhD student, you're not going to have a good time, right? You just have to do that. At least for me, when I was, taking classes, okay, you're studying for a class in your undergrad or master's program, and eventually there was an exam, and okay, sometimes people fail, but overall, you just kind of put there enough, and then it's sort of fine, right? And then it ends, and you have the next class, and so on. But with something like pursuing that research degree program, one thing it really pushed me on was just taking ultimate ownership of whatever thing was on my plate, and not just being like, yeah, I don't know how to do it, I'll ask my tutor, because then there is no tutor, right? If you're a PhD student, you're supposed to be one of the more knowledgeable people in the world in that field. Now, might not be that way in practice always, but certainly the absolute expert in that field might not feel like spending so much time with you and explaining you all the things that you can't figure out, so they need you to figure it out. So that I would say was uh, the biggest, let's say, behavioral trait that doing a PhD helped me with. Um, on the technical side, one thing that now helps me in my role as a data engineer at the ECB is I'm just not scared of touching data, right? I don't really mind looking at okay, so this is this ID code and how is it formatted in this other table, and let me do the select here and look and then write this down, right? Because it's been my daily bread and butter for a while I was doing economics, where you have, I don't know, some different input data sets and you need to think about how to join them, right? And in a way, a lot of things in economics that I was doing did have computer science equivalents. I just didn't know the terminology. So, for example, imagine you have a table where for each country and each year you see the GDP or whatever it may be, right? So, an economist would call this the level of observation, yeah, the year and country, and a computer science person would call this the primary keys of a table. Okay, so you need to learn this new language, but at least the concept in a way you already worked with, right? If you've joined tables, you must have at least thought about that to some degree. And then on your second question on DSTI, now, there's a lot to talk about, there. Maybe I start with the 2 projects, and then we can see if we can make it a bit broader from there. So first of all, just the fact that you allow, or not even allow, but encourage students to look for real world outside projects, that is amazing to me. Maybe it's because my undergraduate and graduate degree were in Germany, where German examination offices are very, how should I put it, like, it's very, very important to them that all students do the exact same type of verification or exam, in order such that everybody is treated and graded fairly. And I see the merits of that. But if you think about which program you want to do, you may want to think about, okay, is this my top priority as well, or is one of my priorities that I can work on something that I can maybe showcase in an application, or something where I don't write this code and do this project for HANA, right? I do this for me, right? I do this because I have some outside goal. And the fact that you guys showed a considerable degree of flexibility of what students can do, that really goes a long way. And certainly not every project works out. There were 2 other classes where I did projects that could have resulted in something as nice, but just didn't, because I didn't pull it off. Maybe I got unlucky, maybe I didn't have the time, whatever the case may be, right? So it's not that every project will be amazing, but the fact that you can do them was amazing to me, right? So that on the, let's say, outer scope of things. And then on the inner scope of things, yeah. So, it always depends on what you benchmark it to. But I think one thing that DSTI excels at is, I think The Economist, or which outlet was it, named data scientist the sexiest job in the 21st century or whatnot, right? And ever since, there's been this hype, right? And there's this massive amount of online courses on data science and this new AI tool, and now it's generative AI and all that. And you teach these things, right? But I feel most classes online that I saw, or some of them that I took before, they did the kind of mistake that I highlighted in the first presentation, where you have some data set, typically some CSV or Excel dump. You read that in your pandas, and then you immediately turn to the model and you do some model tuning, and now look at change, and that's all great. And it's very sexy, I get that. But really, if you work in the industry just for a couple of weeks, you realize this is just never the problem in the industry. Okay. In the industry, the problem is building production grade software systems. Okay. Now, maybe with a data focus at DSTI, that's fine, right? And for the people that want to study here, me as well. Like, I'm not a front end expert. I really don't care much about that part, but I understand we need front end engineers. But for the data side of it, right? I would just encourage everyone to think about the engineering in data engineering and not just the data, even though I understand, like, this is what gets most of the spotlight of it. So to provide example again from the from the slides earlier, right? In the first presentation, I explained how you should think about this data type conversion, right? Or that you should use Parquet instead of storing things as text files, right? This, for example, was one thing that was taught in the what's it called now? I think the class is called Big Data Hadoop Ecosystem, something like this was taught by some of your colleagues, yeah. And this is stuff that's there, right? So I think many of us have seen this picture online of like an iceberg that's in the water, right? And you see this tiny bit that's above the sea level, yeah. That's like shiny data science air bit, but then there's this big thing down there, which to me is the data cleaning side. But then importantly, also building the application production grade systems, right? So that you, as a data engineer, you need to know a little bit about software engineering, right? If you start in this field, you don't know what, let's say, singleton pattern is or a factory pattern is, that's not so ideal, right? If you don't know how a DevOps pipeline works, if you've never done this in practice, if you've never spun up resources in Terraform, okay, you can have some nice jargon on AI, but really what we need more is good engineers. And this was, when I looked at the curriculum, what was it now, 3 or 4 years ago, was the reason why I ultimately decided to study at DSTI and not at other schools, of which there are plenty that offer these type of degrees now, right?
Thank you, Jannic. Niraj, you maybe want to add something about the courses, or
Yeah.
anything about the that relates to Yannick's journey, which can be, I think,
Yeah.
a very good example for anyone aspiring to study, to have a career in data or to study data engineering in general. Let me just say, before I hand it to you, Niraj, that what you said, Yannick, is very true for data science, that it's a very sexy kind of job where we can showcase things very quickly. We often have this problem in data engineering because it's the boring stuff, right? You even said it yourself in a part of the presentation, and a lot of people don't want to look at that. But the simple fact of showing an end-to-end project with the focus on the data part, I think hopefully will go a long way in helping and demystifying a little bit what data engineers really do.
Yeah, and if I can just jump in there, Josh, and then you go in a second. I think whichever profile one picks, right? If you're a data engineer, if you're a data scientist, there's a lot of value in looking at what the other guy does, right? So, for example, if you are a data engineer, but you cannot be bothered to look at what this data actually means, right? You're gonna have a terrible time thinking about like how do I join this data, right? If your Spark job is crashing, because there's data skew, well, yeah, maybe you should have thought about what kind of data that is and where there might be some likely skew, right? But on the other hand, if you're a data scientist and you do the shiny things, do that, fine. But try to, as much as possible, learn about data engineering so you can bridge these gaps, right? It seems to me that most of the value that's left to be reaped out there is there's a data science team, data engineering team, and not just that, right? There's a security team, business team, ops team, all these things, right? But they don't talk enough, right? And if you can bridge that gap, this is what's really valuable, right? And this is why I think this overlap of classes that we share with DSTI between, let's say, data analysts, data scientists, data engineers is quite valuable, because it does help, let's say, someone who studies data engineering like me. I do understand a bit better than how does a data scientist talk about that, or I do know a bit better like the data analyst is maybe not that technical, but maybe he knows that much SQL. It gets me more of a feeling for how we can sort of speak the same language to solve a problem that will be bigger than any individual one of us can solve, right?
Awesome. Thank you. Thanks, Yannick, for this wonderful discussion. One question I have: we do offer a lot of flexibility in the sense that we offer full-time programs for those students who are just out of their university or their colleges, like very young, not much professional experience. We offer them full-time courses. But at the same time, for professionals like you, at the place where you were, we offer accelerated pace courses as well as SPOC, right? So SPOC is self-paced online course. Uh, in accelerated course, people can come to DSTI, study here for 9 months in a very rigorous environment, and then can find internship or job. Specifically, when you are professionally, you have like 5, 6, 8, 10 years of professional experience, and then you have SPOC, which is where people actually do not leave their jobs and study on Saturdays and Sundays, and you chose SPOC, right? So tell me about it. Why did you exactly choose? Did you consider the other, options as well of studying at DSTI? And how did you arrive at the decision?
Yeah, sure. The short answer is no, I didn't really, because I was looking at. Okay, let me take one step back. Yeah. So as I mentioned, I think somewhere in the beginning, I started a bit more on the business side, though always as sort of the most technical person in the team, right? Working on
Mhm.
data engineering problems, but on the business side. And I realized eventually, okay, everybody is super happy that they have me the team to do these things because they didn't want to do them. But at the same time, let's say the managers in the business area, they don't care so much about it. And that's fine, right? That's their job. But I realized that for me, this is going to be then a bit of a dead end. So when I move into tech, and I did feel like having a proper technical, engineering type credential would help me a lot to do that, right? So then I was looking into different options, what there were, and I was thinking about, okay, there's these gazillion of online programs, uh, even like proper master's degrees like yours, right? It's so many schools. Which are the ones that I can do? And because there's so many, I first did a list of things that are not negotiable for me. And one was really that I can do it online, first of all, and secondly, on my own time. Because I just knew my let's say family situation would not allow me to move anywhere for 9 months. Also, it would be very difficult to pause my job or even give it up and try to find a new one. That was just not a very appealing option to me. And then about the self-paced mode, the role that I was in at the time when I made the decision, the workload fluctuated quite a bit, right? So I knew there were going to be entire months where I couldn't do anything towards my master's degree, right? And if this were a problem for that school, then what can I do? It's out of my control. But then other months, I did have quite some time, so I could actually really push forward. And it would be very annoying if they tell me, no, no, you have this one class now, but you can't do a second because you have to have this other one first, or whatever shenanigans some institutions pull, right? So that already was limiting the circle of programs quite a bit, right? And then there are other factors. For example, price, of course, is one. For example, I saw there was a online masters in data science from UC Berkeley. I mean, that is one of the best institutions in the world. But they wanted to have 70,000 US dollars, which I found to be a bit a lot, right? Like I just don't have that kind of money sitting around to spend on that. Okay, so then these go out. And then honestly, the decisive factor in the end between the remainder of programs was what I tried to describe earlier, which was which programs just sell you the sexy bit and which programs go really hard on the engineering bit, even though they know it's not as appealing, is not as sexy. Then you lose some of the modeling bit, but really you learn things like CI/CD pipelines, you learn things like Kubernetes, you learn things like Terraform, right? To make sure that that is part of the curriculum. That, let's say, is not just some theory lecture, but is up to up to date industry content. So, for example, okay, you can have a class on cloud computing, but then why not do it the way that you guys do it at DSTI, where you say, okay, let's do one for AWS, let's say, and you can do an exam, but you can also do the certification, right? Which is great. So having something that's um, focused on the hard engineering bit and is really up to par with what's demanded in the industry, right? That were in the end then for me the decisive factors.
Awesome. So basically, you looked at almost a lot of things. Like you looked at the way your classes are going to be paced. You also looked at curriculum, you looked at price, and after that, DSTI turned out to be the best school. When you compared, I mean, just out of curiosity, over here, when you compared all the curriculums, what stood out for DSTI? I mean, you
Yeah.
have already explained it a bit, but if you had
Mm.
something to add to it, probably, or
Yeah.
something
Yeah.
to consolidate your points on, yeah.
I mean, first of all, maybe I should mention I stopped doing research on this 3 years ago when I enrolled at DSTI, because when I was committed to it, okay, I really look for other programs. But so yeah, take it with a grain of salt and do your own research for sure. But back then, again, really most programs were, first of all, they were literally called masters in data science, and I definitely wanted to do data engineering. So there was just very, very few even in that space that would look at these things. Then of what was there, like in the data science field, I looked at some of them and I had the feeling that some schools took some of their existing classes and they renamed statistics 101 to data science 101, you know? And then they had application fields, and then the econometrics class that they would teach to any econ graduate, the data science people should also take it. And the I don't know, statistics for psychologists, they renamed to psychoanalytics, and then the data scientists were also supposed to learn that, right? And I felt like, yeah, you're just kind of recycling what you have already as a money machine for your department, and I'm not gonna have it. So I wanted to look at something where people really genuinely sat down and thought about, okay, what are the skills that you need in today's industry to do well, and how can we teach that to people best, right? And yeah, that in the end left DSTI as, for me, being the best choice. Now look, I'd be more than happy to admit that it really does depend on the person, right? There might be some other factors that may make other schools better for other people. Like, for example, there's Technical University in Munich. They have an awesome data engineering program, but you have to do it in Munich and you have to do it full time. So it just wasn't an option for me, right? If that is an option for you, maybe that's interesting as well. But if you want something that's really that you can do online, where you have all that flexibility, I think is one of the best options out there.
Awesome, thank you. Okay, so guys, if you have any questions, those who are live with us right now, please ask your questions. We would be more than happy. Otherwise, from our side, we have asked our questions. I mean, Hannah, do you have any other questions to ask?
No, I just wanted to thank you both again. Thank you,
Yeah.
Jannic, for taking the time to give us this overview of your achievements and how it links to your studies at DSTI. I think for us, speaking from the faculty perspective from DSTI, it's always our pleasure to see how the people who pass through the doors of the school can correlate what they see in class with what they really do. And it's awesome that, again, you were able to put this in real life projects, in a real great projects with a lot of value. And Niraj, thank you for hosting this as usual.
Thank you, both of you. Hannah, being here, though you had some classes and you have quite busy schedule, I know. And Yannick, thank you. We have been discussing this for a very long time now, probably since March or April, and you have been very patient. Thank you. Thanks a lot for your everything.
Yeah, thanks a lot for having me. It was a pleasure, and hope to speak to you guys soon. Yeah.
Hope we also hope that. Thank you.
All right. Bye bye. Bye everyone.
Bye.